So, for question 2, very quickly going to go through this. Standard enthalpy change of formation, one of the definitions you have to know, enthalpy change when you form 1 mole of a compound from its constituent elements, with all elements and products being in their standard states, 298 Kelvin, 100 kilopascals. Okay, you just need to learn those ones. Use the data from the data table to calculate standard enthalpy of formation of liquid methylbenzene, which is C3H8, doesn't that say? It's not very obvious, it'd be more obvious than yours. C7H8, C7H, oh, it's benzene, yeah, C7H8. Okay, so it's got these values here for the enthalpies in combustion, and you're calculating the standard enthalpy for formation. Okay, they don't give you very much room to make a cycle here, but I would want you to do one anyway. What you've got to think, first of all, always write down the equation that you're wanting to work out, the equation that you've got that's happening in, on the flat plate, and then when you're using enthalpy of combustion or enthalpy of formation data, you're going to write those as the things you go down and do to make whatever here you're going to make the combustion products. Okay, so here's let's make it around their equation for simplicity. We've got here's the equation that we want. So this is delta H of reaction that we want to find out. We're going to burn all these things. If we burn everything on the right side, it's going to be exactly the same products as if we burn everything on the left hand side. So we're going to burn carbon. It's going to make 7 CO2. We're going to burn hydrogen. That's going to make 4 H2O. Now, if we burn C7H8, it would also make 7 CO2, 4 H2O. Okay, it's going to make the same combustion products. So, if we want to make this, let's put in the values for those. Might as well put in the values right now. So, we're burning 7 moles of carbon, so it's going to be 7 times this minus 394. You can write it neater than me. And here we're going to burn hydrogen. So burning hydrogen, 1 mole will get minus 286. So we're going to burn 4 moles, so we need 4 times that amount. 4 times minus 286. And then we're going to burn this methylbenzene. You burn 1 mole of that, you get minus 3909. It's a big molecule, so you get more. Okay, so but you're only burning 1 mole, so we're going to use minus 3909. 1 times anything is itself. Okay, so delta H reaction. Again, we're going to do the same old start finish. We're starting here, we're finishing here. I'm going to say that going from start to finish, the delta H of the reaction equals, which is the enthalpy of formation of liquid methylbenzene, is going from start to finish. Also going from start to finish, we can come here, down here, and then back up here. So we can go this way around the cycle, so with these arrows, so we can use the positive of 7 times minus 394. See how I've written in the positive there and the negatives there, they're going to come out in the calculator when they do it later. Here, the positive, because I'm going with the arrow again, of 4 times minus 286. And here we're going against the arrow, so we're going to go the negative of negative 3909. So I'm literally going to do it again, negative brackets negative 3909. If I write that in the calculator, it will do the negative things for me. I just need to make sure I write everything down carefully and put it in the calculator carefully, and it's going to get the right answer. I always have a look at the end to make sure it makes sense. So, positive brackets 7 times minus 394. So 7 times minus 394. Close brackets plus, because we're going with this arrow as well, 4 times minus 286. Now negative, because we're going against arrow, the negative, open brackets, negative 3909 for the benzene, for the methylbenzene. That's going to equal plus 7. It says 7, so that means plus 7, and we always write in the plus just to make sure it's obvious. Okay? So the delta H of this reaction is plus 7 kilojoules per mole. Don't forget the units there. Okay? So plus 7. So actually, even though we've burnt all these with loads of energy, and we're burning this with loads of energy, the difference between the standard, the stability of carbon and hydrogen gas to this is very small. Okay? And it's slightly endothermic as well. Okay, to form that. Okay, so that's one kind. We can always have these. If you've got one where you give an enthalpy of formation data, do exactly the same thing. Okay, but instead of making the combustion products here, we're going to make the we're going to put the things that it's formed from down here and have the arrows going in the other direction. But the same kind of process. You have the reaction you're interested in, then you're going to use this data to go to another place and then back. So D, are we going to do this one? Yeah, we're going to do part D. So we've missed out C. Have a go at C. We're just going to do part D to show how to do Q equals MC delta T calculation as well. So they'll always describe, or they could describe a bit of an experiment. Okay, so here we've got 25 centimetre cube sample of 2 moles per decimetre HCl is added to 50 centimetre cubed of 1 moles per decimetre cubed sodium hydroxide. Quick calculation top of your head here, half the amount, 25 to 50, you've got half the amount of twice as concentrated, 2.00 to 1.00, means actually we have a 1-to-1 roll ratio, so worth just thinking about while you're reading it. Okay, initially at 18 Celsius, that's going to be useful for later. After mixing, the temperature of the final solution, so everything we've mixed together, was 26.5 Celsius. Okay, this is the reaction that's happened, which you could just draw, which you may be expected to draw out yourself, because it's just a simple acid plus base reaction. And using this information, calculate a value for the standard enthalpy change for this reaction. In your calculation, assume the density of the final solution is 1 gram per centimetre cubed. And they've given you the specific heat capacity of water already, which is sometimes called, they don't give it a little symbol in this case. So specific heat capacity of water is 4.18 kilojoules per mole per Kelvin, isn't it? Joules per Kelvin per gram, sorry. Yeah, that makes sense, yeah. So we've got all this data and we want you to work out standard enthalpy change for a reaction. Okay. So the equation you're going to use for this is Q, which is the heat change, equals M, the mass of the thing you're heating up, C, which is this, C is the specific heat capacity of water, and then delta T, this is the change, delta always means change in temperature. Okay, so let's think about what we're doing here. The mass of whatever we've heated up is going to be the total volume of the liquid when it's mixed together times 1 gram for every centimetre cubed. Okay, so because this is a density of 1, every centimetre cubed you have weighs 1 gram. So if I have 25 plus 50, then I have 75 centimetre cubed, I have 75 grams. So here, 75 is how much stuff I've heated up. Remember, because we've mixed them together, we're going to have to heat up all that stuff. C is 4.18. The change in temperature now is going to be the final temperature minus the initial temperature. 26.5, that's what we ended up at, minus 18.0. Okay, so our amount of heat given out by however much of this reaction we had, our overall amount of heat, just given in joules, because of C is in joules per Kelvin per gram, and you've used grams, and this is going to be in Kelvin, and this was in joules per Kelvin per gram. The Kelvin cancels out, the gram cancels out just to leave joules. It's going to be 75 times 4.18 times brackets 26.5 minus 18, those brackets equals, so we have made 2,664, actually that round, well let's draw it all out until we give the final answer, actually 64.75 joules. Okay, I'm going to, before I forget, change that into kilojoules straight away, because I'm going to want to give them a value in kilojoules per mole. That's what we normally find when we have standard enthalpy changes. We normally give them in kilojoules per mole. So that's going to equal, divided by 1,000, 2.66 475. Let's keep the big number until the very last moment. Kilojoules. Okay, so that's how many kilojoules of energy was given out. So this is how much energy change. Remember, at some point you can do this at the end, or you can do it now. You can think, okay, this was the amount of energy given out. So was the reaction exothermic or endothermic? If it's giving out energy, because we've observed this energy given to the water, actually it means it was exothermic. So as far as the bonds are concerned, as far as the molecules are concerned, they've lost energy, so it's a negative change. So at some point, I would do it right at the end, you need to go negative because it's exothermic. So whenever you want to do that, you need to have a little line saying, this is a negative enthalpy change because it's exothermic. So this is how many kilojoules. Now we need to know how many moles have reacted. We're using the standard change for the following reaction. Here we have 1 mole reacting with 1 mole. Because we're using exactly the same amount of moles of hydrochloric acid and sodium hydroxide, you just need to choose, if one was bigger than the other, you'd choose the smaller one, you'd choose the limiting reagent, but they're exactly the same, so let's just choose the hydrochloric acid. We're going to find how many moles of hydrochloric acid reacted to give this amount of energy, and then we can divide this amount of energy by it to get the kilojoules for every 1 mole. Okay, so moles here, we have volume and concentration. So let's do it here in a different pen. Moles of HCl equals the volume, which is 25, divided by 1,000 because I want to get it into decimeter cubed. Volume times concentration, which is 2.00. Okay, so it's going to be 2 times 25, so it's going to be 50 divided by 1,000, which is 0.05. But 0.05 moles has released this much energy. So if I had 1 mole, I'd reduce lots more, wouldn't I? I'd produce how many times more? 20 times more, probably. So let's try. What we have to do is get the kilojoules and divide it by the moles to get kilojoules per mole. Okay, so we're going to have now that equals 2.66475 divided by 0.05 equals 0.75 divided by 0.05 equals 53 points, and now we're going to give our final answer, so we're going to give to the right accuracy. 1, 2, 3, 1, 2, 3, 1, 2, 3, all the way through 3 significant figures, so I'm going to give to 3. So I'm going to give to 53.29, so 3 rounds up, kilojoules per mole. Okay, so always now, remember, you're going to work out how many joules by Q equals mc delta T, then we need to divide it by 1,000 to get the kilojoules, then we need to divide it by how many moles we have actually reacted to get the kilojoules per mole. And that's that kind of question done.